The extreme further.
All right, magnetism is caused by charges in motion. With a permanent magnet, the motion of the charges is due to electron spin. Let's review quickly the field around a bar magnet, because that's an important configuration, because we're going to see that there's other things that behave like bar magnets. When we talk about magnetism, we're usually going to use compasses. And a compass is just a bar magnet that's allowed to rotate. It aligns itself in a magnetic field. So the direction of a magnetic field is defined as the direction a compass points when in the field. So if I had a bar magnet like this, and let's say this is north and that's south. So what would the field look like? Well, let's use the compass to aid us. And the idea of basics, some of the basics of magnetism is that north and south are attracted to each other. North and north are repelled, south and south are repelled. So, for instance, if I took this compass and put it right here, it's going to align like this. The south end of the compass is going to attract to the north. The south end is going to attract to the north end of the magnet, the compass to the magnet. Because remember, this is just another magnet, right? So this is going to, the field here is going to be that way, right? Because that's where the compass is pointing. Now, if I put my compass here, what would happen? Well, north attracts to south, south attracts to north. So it would turn like this. So we would kind of point that way here. And then if I brought it here, it would point like this. So we end up with, field kind of like this, going like that. And keep in mind the distance, but these are field lines. And they help us to understand what's happening, and technically they're imaginary. But you kind of get stuff that looks like this. Now that's not so good. I don't like that one so much. I want to make sure that they're closer at the poles and farther apart here. They're a little parallel here, so I don't like the one I just drew. So I'm going to erase that. This one's a little better because it's farther out here and closer here. So let's do something maybe a little bit more like this. I should have better symmetry. It's kind of tricky to draw these things. And then we would have something like this. Gets wider, farther apart here, and closer together at the poles. And these are the field lines outside the magnet, and I ran out of room here. So we get something like that. Keep in mind, these always form closed loops. So within the permanent magnet, these lines would be like this. And they can never touch, and they can never cross. Because if they touched, that would imply an infinite field, because the distance between them is something like that. So make sure you kind of have the basic idea of how to draw the magnetic field lines around a bar magnet, and use a compass to aid you in your reasoning, right? If I were to slap a compass here, north attracts to south, south, so it's going to turn sideways. So any fields out here are going to be pointed this way. Clearly, if I put it near one of the poles, you can clearly see that this is going to turn like this. South is going to attract to north, and the field is this way, right? Going through here, because when you come around, these fields are all pointed that way. And then at this end, if I were to put my compass here, it would point in like that, right? Just like that. All right, So the field around a bar magnet, keep in mind, all magnetism is caused by moving charge. In this case, the moving charge is electron spin. Now keep in mind, we draw this in two-dimensional space because that's usually what we have easy access to. That's our easiest way to communicate with a whiteboard or a sheet of paper. It's a two-dimensional space. This occurs in three dimensions, as you can see in this video, where I have magnetic filings that are hanging out in glycerin. And when I put the magnet inside of it, you can see that the iron filings turn into little magnets and they align with the magnetic field. And you can see the shape of the magnetic field around a bar magnet, similar to what I draw, but it's occurring in three dimensions, right? It's a three-dimensional phenomenon, this magnetism, but we express it in two-dimensional space because that's what we have easy access to when we communicate. We don't have an easy way to communicate in three-dimensional space. You know, papers are two dimensions, and so is like whiteboards. In the previous video, I talked about when Ørsted discovered the cause of magnetism, which was moving charge. It wasn't obvious at the time that that was the case, because all they knew about really were permanent magnets, mostly lodestones probably. So they had permanent magnets, and they didn't know what caused the magnetism. It certainly wasn't clear to them that there was moving charge in a lodestone. There's not, like, you know, which is basically just a rock that's magnetic. And what Ørsted found was, and I asked you to see if you can figure out what the field would look like around a wire. So if I have a wire going here, and let's assume there was current going through it. This one doesn't have current, but let's say that it did. All right. Let's say there was current flowing this way, so we had current going that way. Therefore, electrons are flowing this way. This is the way positive charges would move. But you know, quick review: electron flows this way. Therefore, the current is that way. And he noticed that if he had the current going this way, it would cause a compass to reorient itself. So if the compass was normally like this, and then he turned on the current, what would happen is the compass, if it was above the wire, would point like that, right? And if you put it below, it would arrange itself so it was like that. So what must the field look like around a wire, right? If it, you know, you can reasonably, well, you got symmetry around the wire. We got current going like this, and you figure we probably have some sort of symmetry when we go around the wire. And if it looks like that when I put the compass below the wire, and like that when I put it above the wire, hopefully you could reason that, well, this is a circle, right? A circle would do this, right? This is a circle where you have kind of, you know, if I were to draw it, now we get into trouble with this trying to express three dimensions in two-dimensional space, which is one of the things that makes magnetism kind of tricky. So we have these loops going around like this. The magnetic field line forms circles around the wire, right? It was this way on this side and this way on that side, right? So a circle would do that. We didn't actually measure it. We measured above and below. We didn't measure on the sides because that's not easy to do with the compass, because you would have to turn it sideways. That would make the bearing bind in the compass. A compass only works if you hold it flat. If you hold it like this, it doesn't really work because it binds the bearing. Usually if you're using a compass, you want to go this way anyways because you want to know which way is north or south on the earth, right? So here's a video to show you that indeed you can see that the magnetic field around a wire forms closed loops. Here we have a setup to see if we can figure out what does the magnetic field look like around a wire carrying current. So what I've done is I have a power supply here, and you can see that I have a wire coming out, and it comes through here. And then what I have is I have it going straight down through this white piece of foam core, and then it comes out. It's going to go into an ammeter, then out of the ammeter and back to the power supply. On top of here, I have compasses, compi. So I have compasses around there, and if we take a look here, we can see that they're all reacting to the magnetic field of the permanent magnet I have here, and then when I let them go, they all just point magnetic north. Right. Okay, so let's see what happens when I turn on the current. Again, the current is going to be going straight down through that wire. So we have a current going down through the wire. All right. We can see that the compasses have rearranged themselves, and if you look carefully, you can see that they all kind of are pointing like this, like they're making a circle around the wire. Let's see what happens if we change the direction of the current. So right now the current's going down. Let's see what happens if we make the current go up. So I'm going to need to change my ammeter. Since I'm changing the direction of the current, I need to switch the leads. Otherwise, the meter will go backwards, and it has nowhere to go backwards. All right. So I've switched the leads. So now the current is going to be coming out of this wire into the ammeter, out of the ammeter, and then up the wire, and then back to the power supply. So let's see what happens. And oh, the compasses are not pointing in the same direction as they were earlier. We can see that they switched. Getting closer. All right, so now they're forming a circle that's kind of going like that. Right? So it turns out that when there's current flowing through a wire, the magnetic field lines form closed circular loops around the wire as current flows. And we're going to learn this, what's called a right-hand rule, which is going to teach us, it's going to be it's like a trick, a way of knowing what is the direction. Is it, is the current going this way or is it going the other way? And there's this convenient right-hand rule that'll allow us to determine how that works. All right, so let's see how we could figure out if we have current going through a wire, the direction of the magnetic field around the wire. What we're going to do is you're going to take your right hand, and you have to use your right hand for this. You're going to take your right hand, and what you're going to do is you're going to have your thumb pointing in the direction of the current. Now, in this case, the current was going up, so I'm going to have my thumb pointed up in the air. And when you do that, if you wrap your fingers around it, and your fingers wrap in the direction of the field, so the field was going around like this, right? So my fingers are wrapping in that direction. All right. Okay, and then likewise in the case where the current is going down, so I've switched the current, and it's now going this way. And what I'm going to do is my thumb is going to point down, and my fingers will wrap in the direction of the magnetic field, right? My thumb is in the direction of the current's going down, and my fingers are wrapping in the direction of the magnetic field. The magnetic field's going like that. So that's how we can use the right-hand rule to determine the direction of the magnetic field around a current-carrying wire. All right. So how do we deal with this difficulty of expressing three-dimensional space in two dimensions? Because we can try and draw perspective, but that can get tricky and confusing. And unless you're a skilled artist, a lot of times it doesn't work out real well. And, you might not be able to figure. Sometimes we do that. Sometimes we try. But there's another way to do it. And that is, we're going to use what's called an arrow convention. So rather than try and talk about 3 dimensions and draw 3-dimensional space, we're going to draw everything in 2-dimensional space. But we need to have a way to communicate things going into the board and out of the board. We need a convention for that. And the convention that's commonly used is called the arrow convention. It's like if someone, like you're in the Hunger Games or whatever, and you're firing arrows, what does an arrow look like if it's coming towards you, right? You're out there doing the Hunger Games thing, there's people hunting you down, and there's an arrow coming, you got to duck. How would you recognize arrows coming at you? Well, an arrow coming at you, you just see the point. So that's an arrow coming at you, right? Let me use black. I'm going to use black. There's an arrow coming at you. So this is out of the board, right? This is something coming out of the board. The arrow is coming at you. You're seeing the point of the arrow, right? If I want to describe something going into the board, what are you going to see when the arrow is going away? You're going to see the feathers, right? The feathers. So there's our feathers, and this is into the board or into the plane or the piece of paper or whatever. In this case, I'm using a whiteboard. So it's into the board or out of the board. That's the arrow convention. And it turns out there's as you saw in the video, there's a right-hand rule that allows us to figure out the direction of the circle of the magnetic field around a wire. And what we do is you gotta take a right hand. So why don't you try this? Why don't you grab either if you got a hunk of string, or if you have a wire, great. Or if you don't, you can just kind of grab a pencil, and you could imagine that's a wire and it's got a current going through it. And let's say the current's going away from you. So like I have here. So what I'm going to do is if I want to draw what does the field look like around this wire, this is what I'm going to do. I'm going to grab the wire with my right hand, and my thumb points in the direction of the current, and my fingers wrap in the direction of the field, right? So the field is doing these closed loops around like this. So what I'm going to do is, using the arrow convention, right? This thing is doing this closed loop like this. So on the lower portion below here, the field is going into the board. So I'm going to put an X here because the field is going into the board in the plane of the wire, and when on the other side, it's coming out. So that describes what the field is around the wire. It's into the board at this plane, because you imagine this is right on the plane, here and here. It doesn't describe what's happening here. Now, in front of the wire, it's going to close loops, it's down, right? It's down, right? But we don't draw that. We're just drawing what's happening in the plane of the paper or the board we're doing, right? So, it indicate that so we got our closed loops here. Like that. So that's how we would describe the magnetic field. Everywhere the field created by this wire, everywhere on this side is going to be into the board, and on that side is going to be out of the board. It's forming these loops, right? All right. So why don't we try another one? Let's say I had my wire and it was doing this. So my wire is it's like that. And the current's going this way. Right? Current's going that way in my wire. Why don't you take a moment, draw this on a sheet of paper, and I want you to draw what's the field doing on this side, what's the field doing on that side. Use the arrow convention to do that.
Pause the video now.
All right. So hopefully you're confident. Well, let's see how we did. So I'm going to take my right hand and my thumb points the direction of current. And on this side of the board, I see, it's going to do this. I see that it's going into the board on this side. So arrow's going away from me, so that's an X, right? And then on this side, it's coming back. Arrow's coming back at me. That's a dot, right? X dot, X dot, X dot. So that's what our field looks like right around the wire. Looks something like that. All right. Very good. Hopefully that makes sense. I'm going to give you some problems to practice this. In the PowerPoint of your notes, I had a problem. It looked like that. We had a wire, and we had compasses around the wire, and you have to figure out, is the current going into the board or out of the board? All right, so you had 3 compasses, and it looks like they were pointed like this, and then you had a wire right there that was, it's kind of like this, right? It was going like that. And you got to figure, is the current going this way or is the current going that way, right? All right, well, keep in mind the right-hand rule for current in a wire. Your thumb points in the direction of the current and your fingers curl in the direction of the field. Now, what I'm going to do here is I'm going to draw the field. I can see the field is like this, right? There's our magnetic field. It's going around like this, right? And the symbol we use for magnetic field is B. It's a vector, actually. So going like this. So my fingers curl in the direction of the field. So it's going like that. So going like that. So the current that was causing it must be coming out of the board. So since it's coming out of the board, I'm going to put, running out of battery. I'm going to put a dot right there. Let's try another example in your notes. Just make sure we got this right-hand rule right. You had one, looks like this, where we had a wire from the side, and we had magnetic field that looks like this. Looks like that. So which way is the current traveling in this case? All right. So we're going to use the right-hand rule, and the current's either going this way or that way. Why don't you take a moment to figure that out?
Pause the video now.
All right. So let's try this out. I got into the board on this side, out of the board on that side. So it looks like it's going around like this. So the current is going this way. Current through the wire is going that way, going down, using the right-hand rule, like that. All right. Let's say we had a loop of wire like this. Here I have a loop of wire. Let's say we had a battery like that, connected like that. I'm going to draw here with some sort of voltage source going like that. And this would be the positive end of the battery. So we would have current going around the loop like this, right? Goes through the battery. All right. I want you to figure out what is the field going to look like inside the loop and what is it going to look like outside the loop. These loops are going to be real important in magnetism. So I want to take a moment to do that. Use the right-hand rule and figure out what's the direction of the field inside and outside.
Pause the video now.
All right. So here you go. I'm going to take my right hand. The current's going this way, so my thumb is going to point in that direction. And I see that anywhere I go, and I got to go around this way, it's going to be into the board in the middle, right? It's going to be into the board, so I'm going to put, I guess I'll use black. I'm going to use X, boom, boom, We're going to have these closed loops, circles, around like that. Going to go all the way around. Boom. In on this side, out on the other side. Right? All right. So hopefully you got that down, because this is a real important configuration. And now what I want you to do is think about this. What would happen if we took this and instead of having just one loop, we had two loops? So I'm going to loop that around again. Let's see what would happen. So now I have my loop. I had to make it smaller because I ran out of wire. Let's assume it's the same size. Let's say everything's the same, except now I go around twice. The loop goes around twice. We still have our battery. And our battery is still going like that. So we still have our current going around like this. So what I'd like you to do now is we got two loops. I would like you to draw the field, and if you got two colors, that'd be great. I'm going to use black and blue, I think. Blue, right? Yeah, I'll use black and blue. So first time around, why don't you draw the what's the field look like in red, and then in the second time around, go in blue. All right?
Pause the video now.
All right, here we go. Current goes around once and then twice. So the first time around, into the board. We got something like that. All right. Goes around, boom, out of the board on this side. Okay. Second time around, right? It's going around, and the current's going the same direction the second time around. So what have we done? What have we done to the field by going around twice? Right? It's in the same direction in the center. It's in the same direction as the outside both times around. What have we done to the field by going around twice? Well, you can see we've doubled it. We've doubled the field, right? So if we had a field of 1, of magnitude 1 on the first time around, 1 Tesla, which is really big. But anyways, 1 Tesla around. The second time around, it would have like 2 Tesla. Twice as much. And then 3 times around, it would have 3 times as much as the first time. And 4 and 5 and 6, right? This is an important configuration because it allows us to concentrate magnetic fields. It also allows us to efficiently capture magnetic fields. So we could loop this around a lot of times like that, right? And it's kind of a haphazard sloppy coil. But when you're doing this stuff big time and you want a lot of turns, you use something like this. You make it nice and neat. This is a coil. This is called a coil, or more formally, a solenoid. A solenoid is the term we use when we have a coil of wire that's used in magnetism. It's a solenoid or a coil, also called a coil. And we're going to learn a new right-hand rule for determining what does the field look like as a solenoid. Now, one thing about a solenoid too is that the magnetic field that it sets up looks like a bar magnet. It has a field that looks like a bar magnet. So this can be used as a replacement for a bar magnet. And understanding what a field looks like around a bar magnet is going to be important, because you're going to be able to transfer that to a solenoid, because solenoids are important in magnetism. So let's learn a new right-hand rule, for a solenoid. So a solenoid, you're going to have current going around either this way or this way, depending on how the battery is connected. In this case, it was going around this way. So if this was more turns on this, it would be going around this way. What you do is you take your right hand and your fingers curl in the direction of the current. So in this case, if this was my solenoid that I just had, the current is going around like this. So I'm going to curl my fingers this way, and your thumb points in the direction of the magnetic field inside the solenoid. So in this case, I go like that, and indeed, that is the direction of the field inside the solenoid. It is into the board, right? Right? So that's important. The right-hand rule for a solenoid. Your fingers wrap in the direction of the current. Your thumb points in the direction of the magnetic field inside the solenoid. So let's take a look at a problem like this. Let me draw a side view of a solenoid, and I'm going to draw. Here's a core. Very often, their solenoids are wrapped around like the little electromagnet that I wrapped around the nail. That was a solenoid, and in that case, we had an iron core, and that iron core actually made the field larger, because what it did was when the field was set up by the wires, it caused domains to line up, and you had the magnetism due to the spin of electrons, plus you had the coil. But let me draw this coil here. Here I have the wire coming around the back and going in the front. So I'm drawing a very loose coil so you can see how it's wrapped like that. And let's say the current was traveling this way in that case. So we had current traveling that way. What would the field look like around this? So I'm going to use a right-hand rule for a solenoid. So here's my solenoid here, and the current is going like that. I'm going to take my hand and wrap it this way. So my thumb points in the direction of the field inside the solenoid. So inside the solenoid, I've got a magnetic field going this way. Now, of course, it's going to form closed loops. So it's going to come out, and it's going to circle around and come back, right? It's going to be that way here. And if I do another one, it'll go like this. So this ends up looking like a bar magnet, right? So there you go. That's what the field would look like in that solenoid. Now, why don't you take a moment to draw that, and why don't you draw that's a bar magnet, basically. So why don't you draw the north and south poles on this?
Pause the video now.
You really should create yourself a little compass. All you need is a little sheet of paper with an arrow on it. Right? That'd be your compass. Help you with your thought experiment. Really makes this stuff easier. So, as long as you understand how a compass works. So if I put my compass here, it's going to align with the magnetic field. The magnetic field is this way, right? It's coming out of this end. So it's pointing that way. And this end is attracted to that end. This is the south. It's attracted to that end. So that end must be north. This must be the north end of a bar magnet right here. Right? And then if I took it here, the field is going in, right? So the north end is pointed that way. The compass is pointed that way. So if north is attracted to this end must be south, right? So there's our bar magnet, north and south, caused by that current. Right? All right, that is the right-hand rule for a solenoid. That's going to be an important idea. We have one more right-hand rule to learn, and this is an important one. And this has to do with charges moving through magnetic fields. If a charged particle moves through a magnetic field, it may experience a force. And this is an important idea because this is at the heart of electric motors and electrical generation of power, right? That allows us to have the modern world we live in. If we didn't understand this, we wouldn't be able to generate electricity. So let's take a look at that. All right, let's imagine we had a magnetic field this way. We'll make it a uniform magnetic field for the sake of simplicity. And let's say I had a positively charged particle with a velocity this way. That particle would not experience a force due to the fact that it's going through a magnetic field. because the direction of the velocity is parallel to the field. It also would not experience a force if it had a velocity that way, because it's anti-parallel to the field, right? So it turns out that the only time a particle will experience a force, a charged particle traveling through a magnetic field, is if it has a right angle component, if its velocity has a right angle component to the field. So therefore, if this was my velocity vector right there, it's going that way, that's going to experience a force, right? Or if it had a velocity this way, this would also experience a force. It just wouldn't be as strong. A component of the velocity vector here is perpendicular to the field, but a component is also parallel to the field. The component that's parallel to the field does not contribute to the force. Only the component that is right angles does. So we need to learn a new mathematical idea, and that's called the vector cross product. And this is how the vector cross product works. If I have two vectors, let's say I had vector A this way and I had vector B this way. There is something called a vector cross product, and it's written like this: vector A crossed with vector B. And that will result in another vector C. And the way it works is we're going to, now in this, when we study magnetism, we're not actually going to calculate magnitudes. We're only going to be interested in direction. So let's talk about the direction. Well, basically, we could talk about the magnitude too. What we're going to do is take the, we're going to break A into its components, and we're only going to multiply the right angle component of A with B, and that will give us the magnitude of C. But I'm more interested in the direction of C. And this is the way the cross product works. You need to take your right hand. It's a new right hand rule. And what you're going to do is point your hand in the direction of the first vector. In this case, A is my first vector. And then I'm going to bend my fingers in the direction of the second vector, which is B. Now, I can't bend them backwards, right? So I'm going to rearrange my hand. Okay? My hand's still pointing in the direction of A, but I still can't bend it towards B. So I get to rearrange it again. My hand's still pointed in the direction of A, but now I'm in a good position to bend them towards B. A cross B, your thumb will point in the direction of vector C. So the direction of C is into the board. So C is into the board. A cross B gives me C, which is into the board. Right? So we're dealing necessarily with 3 dimensions when we're dealing with a vector cross product. So we have to use a Zaric convection. Now, let me ask you a question. Just from don't even worry about the magnitude. So if I had B cross A equals D, are D and C the same? Does A cross B equal B cross A? Give it a try. You can figure it out. I don't need to tell you. This is something you can figure out. If you understand this, A cross B and boom, right? Hand goes in the direction of the first vector. Fingers bend in the direction of the second. Thumb points in the direction of the resultant. So, does A cross B equal B cross A? Does C equal D?
Pause the video now.
All right. So hopefully you found out, no, it does not. It does not. Because if I go B cross A, which way is the direction of D? D is out of the board, right? So it's in the opposite direction of C, right? A cross B does not equal B cross A. It's not like in multiplication, 2 times 8 equals 8 times 2. And it doesn't work with this, right? It doesn't work with a vector cross product, right? I forget what mathematical property that is, but you can't switch the order. No order switching. That's a vector cross product. So it turns out that if I want to figure out the force on this thing, let's just say I had a positively charged particle moving like this. It turns out there is going to be a force on that. And that force can be calculated. We're not going to calculate the magnitude. It can be calculated. We're only going to determine the direction. So, the direction of the force vector on a charged particle moving through a magnetic field is QV cross B. Right? Where Q is the charge of the particle, V is the velocity vector, and it's crossed with the magnetic field vector. So let's take a look at this thing. So I got a positively charged object, and what's the direction of V cross B? Why don't you take a moment, figure that out?
Pause the video now.
All right, V cross B. I got V this way, but I can't bend them in the direction of B, so I go like that, and I still can't. Now I can. V cross B. The force is into the board. So the force vector, which I will draw right here, is into the board. Force is into the board. V cross B into the board. The force on this thing is into the board. So if this was going straight up like this, it would start curving that way. Interestingly enough, it won't slow down because the force vector is always at right angles to the velocity, so therefore it can't do work. It can't change the speed. It can't change the kinetic energy. It can change the direction, though. Now, something interesting happens. What happens? Notice I used a positively charged object. What would happen if I used a negatively charged object? Oop, should have kept my velocity vector. Let's say this was negative. So let's say I had an electron going this way. It had a velocity. It was straight up like that. What would the direction of the force on that be? Right? Well, that's where Q comes in. So first, let's just go V cross B. So I got V cross B, and we decided V cross B is into the board. But Q is negative. That flips the direction. So I would go V cross B into the board, but since it's negative, the force vector is out of the board, right? So our negatively charged object would curve this way, out of the board, right? So there. Go V cross B to figure out the direction if it's a positively charged object. If it's negative, flip the direction. All right. So that is the force on a charged particle in a magnetic field. So let's try a couple problems. All right, in your notes they had a problem that looked like this. So what is going to be the force on this thing? So I'm going to go QV cross B. So V is this way. All right, but my hand's not, it's pointed in the right direction, but it's not oriented right. I have to twist it so that I can bend my fingers into the board. V cross B, I'm going to go like that. V cross B, I'm going to bend in. This is going to experience a force upward. This is going to experience a force that way, right? So if this thing's going, it's going to start turning, right? It's got a force at right angle to its velocity. This is going to be in circular motion, if you remember. Circular motion, that's what causes circular motion. Uniform circular motion, actually. If this was a uniform field going like that, this would just go in uniform circular motion because it has a net force at right angles to its velocity, and it will always go in a circle. All right, the next one had a uniform field, and it looked like it was coming out of the board, and we had a velocity like that. We had a negatively charged object. So what's going to be the direction of the force? Let's see. We got V cross B. I got B's out of the board now, though. V cross B. Would this experience a force this way if it was positive, but it's not positive. It's negative, so it's going to feel a force that way. I'll go black. So this is going to experience a force that way, right? V cross B would experience a force this way, but it's negative. If it was positive, it'd be this way, but it's negative, so that flips the direction of the vector, and it's that way. So there you go. It's not too bad. You have to practice it, though. Can't just watch. You got to do it. You got to use your right hand. Don't use your left hand. You know, it's really, the right hand rule is a disadvantage for righties on tests, because on tests, you're using your right hand if you're writing, and then it's very sad when I'm watching someone taking a test on this stuff, and they're using their left hand. I see them going like this. You go, uh-oh, you're in trouble. You can't use your left hand. You got to put your pencil down and use your right hand. Now, lefties, you're all set, because you're already writing, boom, 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 and you can use your right hand because it's free because you're writing with your left hand. All right? So, anyway, it's mostly a right hand world, right? Righties have advantage over lefties because everything's made for righties, but here are the lefties. It's lefties' revenge, right? Because you can use your right hand rule without putting your pen down. That's efficiency. All right, there are 3 right hand rules. We'll practice that a little bit. I got some activities based around that, and got some interesting stuff coming up. All right, I'll talk to you soon. Bye.
It's Street Physics.